So, warm welcome and good evening, ladies and gentlemen. So, my name is Ronald Root. I'm the business field leader for the business field off-road inside AVL. So, I'm coordinating all activities related to agricultural and construction machinery inside the global AVL network. So, my background is mechanical engineering. Then I worked more than 10 years for a British company, so for GKN, for driveline systems for agricultural machinery. And since 2017, I'm with AVL. And since 2018, I'm here in my current role. This evening I have the great pleasure to present you our internal R&D project about the development of an autonomous electric power chassis for electric tractors. And it's a pleasure to have this opportunity to present you this interesting project in the next 30 to 45 minutes. Well, first of all, I would like to introduce AVL briefly. So AVL is the world's largest independent engineering company in terms of engineering of mobility. So for automotive, for off-road, but also for stationary applications. So we can look back on a long history. So the father of our current CEO, Professor List, founded the company in 1948. So we have more than 75 years experience right now. Meanwhile, the group consists of more than 11,000 people, and 2/3 of them are engineers. And our turnover in 2022 was roughly 2 billion euros. And 12% of this turnover we spent for internal R&D projects. So which finance then also this project, what I'm going to present you tonight. So out of these R&D projects, we build up our internal capabilities and know-how, but also we drive innovation and generate patents. So this year we have more than 1,500 patents in force. So the company headquarters is based in Austria with about 4,500 people. Therefore, also the export rate is 97% because most of our business is out of Austria. Myself, I'm based in the Competence Center for Commercial Vehicles in Germany, close to Düsseldorf. And so we are present in more than 26 countries with more than 45 affiliates and tech centers all over the world. So we, as some of you might know, we have also a presence in the UK. So we have the Engineering Tech Center in Coventry, which deals with ADAS topics, calibration topics, controls and software development, diagnostics, weekly workshops for passenger cars mainly, and also test beds for battery and also ADAS development. Besides the business unit engineering, we have also a business unit instrumentation and test systems, where we design, develop, manufacture, and sell test systems. So starting from single test devices up to complete testing infrastructure, including the buildings. And the third business unit is the advanced simulation technologies. Here we develop tools for simulation purpose of the combustion process or NVH simulations and stuff like this. Okay, coming to the topic of today, electrification in agriculture. So we have here some trends and drivers. So we have the increase of productivity and efficiency. So it was also the topic of last Agritechnica, which took place last week. So green productivity, we have to increase the productivity of the agricultural process and to become more efficient, and to produce more with less. We have also the duty to reduce the CO2, to become more sustainable, and also to give a more green image to the agricultural sector in total. Also, for sure, TCO are quite important. So especially for special applications, electrification could be also positive TCO effect. So, but there are also challenges which come along with electrification. So it's the operating time, there's the range. So usually tractors require a long operating time per day. It depends really on the type and the size of the tractor. So smaller tractors are more suitable for electrification because they have typically quite moderate load cycles, relatively low operating hours per day, and they are operated close to the farm site. So, and meaning close to the infrastructure. So large tractors are operating more or less the whole day, and so with a high energy demand per cycle, and electrification has some limitations. Later on, I will also show you some evaluations what we did on a fleet of about 10,000 tractors across Europe, and the outcome was quite interesting. So charging infrastructure, already mentioned it. So on the farm side, it's possible, yeah. So to charge tractors, but in the field, it's yeah, really a challenge. So the distance, especially the distance between farm and field, has to be considered. But there are also some engineering constraints, like the high diversity of applications, the installation space, yeah, in all the very quite tight packaging constraints, yeah, also the weight, yeah, of the tractors, and the weight distribution is a challenge. So if you package the battery in the front of the tractor, we put more weight on the front axle, and also so the load on the front axle will increase, so which has impact on the traction force distribution, but also on the durability of the front axle. Also, the harsh environment in our industry is quite challenge for electrification. So temperatures, cold temperatures in winter time, but also quite hot temperatures in summer, are challenging, yeah, and need certain measures so that it works. So costs, yeah, so component costs due to the relatively low quantities in our industry are quite challenging, especially for special component development like batteries, inverters, and stuff like that. So, and also the limitations, yeah, due to this different environmental constraints and different applications. So the carry over from other industries like the passenger cars has certain limits, and also the second life issue. So what happens if, so usually a tractor has a second life after a certain period, and here there's also it's important for the farmers. So here you can see some investigations we did on a fleet of tractors between 75 and 200 kilowatts across Europe. So it was a fleet of about 10,000 tractors. You can see here the time-based share. So 25% are standstill, 24% are standstill, 25% transport. Then we have the field work, so PTO, with PTO, and field work without PTO, and about 10% stationary work. What does it mean on the energy-based share? So transport is 35%, so PTO on field work with PTO is 20%, and so then field work, so for cultivation, plowing, stuff like that, so heavy field work is 31%. So 7% is stationary work, and 6% standstill. Just to give you an idea about the usage of tractors all across Europe, so this was a fleet of about 10,000 tractors used from Scandinavia down to Italy, which we investigated for this investigation. So if we now analyze the energy consumption per day, yeah, and the coverage, what would be possible with a battery packaging inside the tractor. So here we used 600 liters volume, so it was 270 kilowatt hours battery inside this tractor, so already quite significant capacity. So we were able, so if we can look, so on the y-axis you can see the coverage with every single vehicle. So, and if we want to cover 100% of the vehicles, you can see that the green bars, which means it can be covered, are quite low. So only 20% can be covered. So, but if we cut the extreme points, and the extreme days, so up to 90% coverage of working days, then there is a significant step so that we can already cover 80% in this power class. So this would meaning 100 horsepower. And if we cut it to 80% coverage of working days, then we are close to 95% coverage in the 100 horsepower class. So meaning, I think this would be, from our perspective, a suitable compromise, and this would be accepted from the farmer, so that from the conclusion is that up to 130 horsepower battery electrification seems to be feasible from technical point of view. And here is therefore I draw this conclusion. So up to 100 horsepower, meaning 100 kilowatts approximately. So this is so 100% coverage is not possible, but with certain compromises, battery electrification seems to be possible. Additional advantages could be generated with autonomous tractors with additional storage space and adapted agriculture processes. So tractors significantly above 100 kilowatts, it's still the AVL perspective, will need some liquid energy carriers and maybe supported with hybrid solutions. But here we see CO2 neutral energy carriers as necessary. So coming to some examples out of the industry. So around 50 kilowatts and below, we can already see some examples. Here you can see on the top left the Monarch tractor from out of the US. Yeah, it's a full battery electric tractor equipped with autonomous functions. So CNH bought some shares of Monarch tractor. In the middle, you can see the E100 from Fendt. Also a tractor which has been first shown on Agritechnica 2017, and it will go into production in 2024. And see all these applications, so for high value crops, like in wine and orchard farming, inside farm buildings, in greenhouses, but also for municipal applications or special applications like this mountain tractor. Also an example, it's from company Rigi Truck, now produced in Italy from in the Goldoni plant. And so these are all examples of full battery electric tractors. So for work inside farm buildings, high value crops. So and there where additional advantages of electrification can come into account and provide an additional customer value, like lower noise, no emissions, and beside the CO2 topic. Yeah, and now coming to the AVL R&D project, the e-tractor development, which we started in 2017. So it's a modular battery electric platform designed for different applications in order to increase the degree of utilization of this platform. So it can be used for different kind of vehicles, in order to make the business case more attractive. So this platform is equipped with brake and steer-by-wire in order to be prepared and ready for autonomous operations. It provides a lower noise level and CO2 neutral operations. It's ideal for municipal applications, but also for compact construction equipment and small tractors. Here you can see in the history of the project, as mentioned. So we started the project in 2017 with a market and product study. So we did a market survey and requirement engineering for this vehicle. And based on this requirement document, we started the concept phase in 2018 and run the concept development, and later on the detailed development of this vehicle concept until 2019. Then we started with the prototype development, so the detailed design of the chassis, and which has been first time presented at AGRE Technica. And in 2020, we had the first functional prototype available and ready for commissioning. And the status today is the vehicle is the functional prototype is up and running and used in some funded projects on the EU basis for intelligent automation topics. So like remote control, but also follow me functions, and also access via virtual glasses. Later on, I will show you some details about it. So here you can see the full electric vehicle with a dedicated eDrive architecture, and that's the main difference to the majority of electrified tractors you can find right now. So these tractors took the conventional powertrain and just replaced the ICE by the eDrive, and we started from the scratch here, and designed a vehicle based on a dedicated eDrive architecture. So we get rid of the constraints coming from the architecture of the conventional vehicle in terms of powertrain architecture, but also weight distribution, packaging constraints, and things like that. And we decided to have a more or less a backbone, a frame in the middle, which carries or consists of all electric components like the battery, the inverters, the cooling system, but also the hydraulic system, so that this platform can be used for different applications. It's has 25 kilowatt motors on each axle, so as a central axle drive, and so it's equipped with brake and steer by wires, and with all-wheel steering. On the platform itself, we can use different what we call system implements. The cabin could also be an implement, like what we call system implement, and we have packaging space which could be used for additional battery pack in the front or in the rear, and some attachments as well. So here are some examples out of the market survey and the research. So we asked several fleet operators of municipal vehicles, but also wine and orchard farmers and potential customers of such kind of vehicle. What would be the requirements in terms of traction power, hydraulic power, PTO, the net weight of the vehicle, the payload, the ground clearance, the track width, turning radius, cab position, and also operating time. And here you can see, so there is a quite big range in some areas. So, and therefore we need it was requested to design a vehicle with a lot of flexibility. And based on this, we derived the target specification, and here you can we did an analysis of the use cases in detail. So we took cycles of different applications, so like weeders or mowers, so with also in municipal applications, but also for agricultural applitions, so with for light cultivation, but also road transport. So these applications have been analyzed in detail, and here you can see some examples of conventional vehicles, and also then the concept design for our vehicle, how this could look like in a later stage. Yeah, the idea was to have a modularity in the system, and to customize the vehicle in its main functions. The combination of different system implements optimized and adjust these operation procedures and make it possible to use the one platform for different applications. So this provide cost savings due to the central power supply and increased degree of utilization of this platform development. So the cabin position could be variable in the front, in the middle, or in the rear. You can see here examples of a sweep application, like it's a mowing truck used in the mountain areas, or here you can see a vine and orchard tractor. So the system itself has a peak power up to 75 kilowatt. Here you can see the first design of the power chassis. Later on, I will go in detail through the different modules and show also an animation about the vehicle itself. So the idea is that the power chassis carries all necessary components to have a platform for different kinds of vehicles. So here you can see the different modules of this power chassis. So it is an electric module showed in yellow, then a hydraulic power unit in blue, pneumatics in green, the cooling system also here in I would say in light blue. Then we have the drivetrain in gray, and also the implement connect here in brown red. Okay, coming to the electric power unit. So it has two motors, one motor in each axle. So on the front axle, one central motor, and on the rear axle, one central motor. In addition to that, we have one e-motor for the hydraulics. So in total, we have a peak power of 75 kilowatt. So 25 for the hydraulics or 20 for the hydraulics, and 2 times 25 for the axles for the traction drive. The system is based on 700 volts, and maximum we can integrate up to 140 kilowatts hours battery capacity. In addition to the traction battery, we have also control battery and a safety battery in order to fulfill the requirements for the brake and steer-by-wire functions. And in the central of the vehicle, we have in gray, so the battery itself. On top there is the power distribution unit, and we have the inverters for each motor, and then also the DC-DC converters here. All the units, so the inverters and the motors are liquid cooled, and also the battery has a separate liquid cooling system. So coming to the hydraulic power unit, so in order to be able to use also the conventional implements, we decided also to integrate a hydraulic system, but also for the brake and steering system, we need some hydraulics. And so we have a 60-liter pump, which operates at up to 225 bar. We have a usable oil volume of 45 liters. And you can see here the tank, here the motor for the pump. The pump is allocated here. Then some valve blocks also for the steering functions and for the brake functions. And the implement power supply for sure. And coming to the pneumatic system, we decided also to integrate a pneumatic unit in order to use also trailer, and a pneumatic trailer brake. Therefore, we have a 445 liters per minute compressor operating at 8 bar, approximately 3 kilowatt, and a reservoir of about 10 liters. Allocated in the rear, here in this area. You can see here the reservoir and the two ports. Well, then you can see the cooling system as already mentioned. So we have the cooling system for the electric components, so that we have the radiator here in the rear, the fan, and there is then one loop for the e-motors and also for the inverter. And we need for this a cooling pump, so it's water glycol cooled, and so it's up to 8 kilowatts cooling power. Well, coming to the drivetrain, as mentioned, so we have two independent axles with two e-motors connected to the center of the axle. So there's, for municipal applications, we have only a single gear stage before the axle. So it's a planetary gear stage which we developed in-house. So we took some Parker motors here. So the rotation kit of Parker integrated it in one housing, connected it to the planetary gear set, which is then directly connected to the axle. For some agricultural applications, we would need a 2-speed gearbox in order to realize the ratio split between maximum traction force and required top speed. So for municipal applications, we designed a vehicle for 30 kph, and so we are able to fulfill the previously shown applications with a single stage gearbox. So we have here different steering modes. So it's all-wheel steering, but could be also not only front-wheel steering, but also crab steering, like it's mentioned here. Variable track width was also a point what we discussed during the market survey, and also variable ground clearance was also a point which showed quite high customer demand, and in the list of demands it was a quite high priority. So it has not been realized in the prototype so far, but there are some concepts how this could be realized, so that we could also the track width and also the ground clearance for the vehicle itself. Well, here you can see the overall specification of the vehicle. Maybe in parallel I can start the animation. You can see here the vehicle itself in the animation. As I explained before, different applications like this municipal application, also for a spraying application. You can see the brake and steer-by-wire system. And here it's for this autonomous driving, and this the idea is also that the farmer could use his own electricity. I hope the video is working via this online meeting. But in general, to summarize the major characteristics of the vehicle, so we have a wheelbase of 1.75 meters, a length of 3.5 meters, a width of 1.2 meters, shipping weight of 1.7 tons, gross weight is 5 tons. So overall system power is 75 kilowatt, 50 for traction, that's only 20 for the hydraulics. So based on 700 volts, and so we have also implement power supply, 50 kilowatt. This is that would for offboarding power, and this would be also the maximum charging power for the battery, in order to have a moderate C rate, in order to take care of the battery. So as mentioned in the beginning, also the target of our internal R&D projects is also to generate some patents, and also this was the case here for this project. So we generated in total 6 patents out of it. So it's for in different areas, like the ground clearance unit, so electric coupling for the system interfaces, but also a hybrid module, and some coupling devices. So these are 6 patents which we generated out of this project. And as mentioned, we used this project also for a purpose to demonstrate our integration capabilities. I think the unique thing is, so we took so more or less all components are off-the-shelf components, except the battery. So the battery is a dedicated development for this vehicle, but all other components like the e-motors, the inverters, the DC-DC, the charger, cooling devices, everything is more or less off the shelf available. And we did all this integration work and alignment with suppliers in order to create this vehicle. And so the purpose of this vehicle is to demonstrate here our capabilities and to use it as a kind of innovation carrier and platform for our R&D projects, and also for marketing purpose. So so we use this vehicle also for autonomous driving and assist functions. Yeah, you can see the vehicle in the bottom left, yeah, as autonomous vehicle. It is equipped with cameras on 360 degrees, and also with LiDAR and radar sensors in the front, and with a GPS device on top of it. Yeah, we do the path planning via the GPS. We have a kind of what we call geofencing system, in order to set the limits of the field. And then the vehicle is capable to do autonomous operations on the field. So we have a lane guiding system. We can do automated headland management, and we can have then also obstacle detections and collision avoidance systems. So in case of if an object is detected, or a malfunction is detected, the operator gets an information and can get access via virtual glasses, check the situation, and via the cloud, and can decide how to proceed. What we have realized here with the vehicle is a remote control, follow me function, this obstacle detection, and a collision avoidance system. So it's not only a nice PowerPoint, it's also, sorry for that. It's also real. You can see it. You should be able to see it here. Now the video is working. So you can see it here in our test area in front of our workshop. This is the configuration. So we removed the covers so that you can see also the internal parts. And it's here in operation in front of our test centers. You can see the different steering modes. And so I think the one advantage of AVL is so that we have work for different industries, and that we are able and capable to leverage some developments from other industries, like this object recognition and detection system, and also classification. You can see it on the bottom right. We developed for passenger cars, and in some areas also some lane detections on the top to track the applications. On the left side, you can see this lane detection for rows in the field, and also this obstacle detection on the tractor itself. So this is something what we did and also applied to this project. So coming to already my last slide. So from our perspective, electric tractors can contribute to sustainability of agriculture, especially for small and compact applications. So semi or full autonomous tractors would help to overcome the shortage of workers. So, and we have proven this, or we have demonstrated the proof of concept of such an autonomous battery electric tractor. And from our perspective, dedicated eDrive architectures and the modularity increase the benefits, so that you get rid of the constraints coming from a conventional tractor architecture, and doing a dedicated development has a lot of benefits and advantages, especially in terms of packaging and the related or the corresponding operating range. So the use of off-the-shelf components decrease the development efforts significantly. So therefore, especially when it comes to these relatively low quantities in our industry, it makes sense to consider off-the-shelf components instead of dedicated component developments. But in some areas, it is needed. But we strongly recommend to use to integrate off-the-shelf components as far as possible. Well, thank you very much for your kind attention. It was a great pleasure to hold this presentation, and I'm looking forward to your questions.
Ronald, thank you very much indeed, sir.